I want to talk you, my talk will be around of this theorem. This is my last result in this research along the several years. This theorem is obtained cohomology theories to solve field equations in mathematical physics. And I have used two ways for this problem. One way is to use D models, quasi-coherent D models, and construct the derivative categories throughout of the shapes constructed throughout D models. And second way is use the tensor products. Yes? Do you hear me?
Yes, sure.
Okay.
Yes, excuse me, what does mean the different symbols of differentials in the third row? D multiplied by D from A is equal to 0.
It's a category, derivative categories. The notation precisely is the second way to solve this problem. I will use the motives theory to solve the problem, to solve these equations in mathematical physics, and use the category I have defined this derivative category as the field equations in quantum field theory. And the problem is to construct and demonstrate the commutative of the triangle commutative scheme for this solution to obtain the integrals for these equations. This is my approach in this study along the several years, and I have many papers published in different journals in the worldwide diffusion. Well, we have the following considerations. We have functors. These functors are constructed through the hard and much work to define these functors, where the L sub A is a Lipschitz functor over on the affine line as a verity. We need consider the schemes as a verities, complex verities in our manifold. Remember, our manifold is Riemannian, complex Riemannian manifold with singularities to solve all equations field theory. The facts for example, when this functors was constructed by Boletsky, Massa, and Aubry, and you can see these details in this work in Clay Mathematics Institute. In fact, for example, we have these theories to characterize the locally constant mapping to define this product, tensor product of the shapes, Italy shapes, which are more convenient for this theory because to affine vertices, which the convenient to define the quantum phenomena. We have the corollary, also Boydowski, and this corollary is very important because define the tensor triangulated categories. Finally, the vanishing criteria for the cohomology spaces. When the cohomology space is vanished, and use the functor defined for these products, tensor products. Remember, our construction will be throughout the tensor product, derivative tensor products, which are convenient or is convenient for define the triangulated derivative tensor structure to our derivative categories. In the motifs context, we have the following results. The first result is a more specific study for the topology, the Zariski topology, which is will be the more convenient for the hypercohomology, to define the hypercohomology in the final process of the Motivic cohomology. The corollary is to define the equivalence between the shapes, the Nisnevic shapes and Etale shapes in Q models, in the context Q models. These Q models will be to define the context of the hypercohomology in this theory. Why Q models? Because the Q models are define the field, the numerical field, more adaptative to the quantum field theory. The proposition 2 and 1 define the equivalence in the cohomology context using the Etale shifts. And theorem 2.1 define the functor, more important functor, to give the equivalence of the triangulate categories in the context of Q ring content in the ring area. Considerations, we have considerations for field equations. By Grothendieck, Beilinson, and Berkelov, we have, there is equivalence between categories. These categories are studied in the derived categories in the Langlands program of ramifications, where the ramifications are connections, where the connections are differential operators which define the field equations. And in this context, this category, Abelian category, is equivalence mode sub B. This mode sub B is a modulus stack studied in algebraic geometry and mathematical physics in the context of the field equations. And it's necessary to define the cotangent complex through or across of the functor. This functor is constructed through of the complex of the differential forms, the product, the tensor product, and B is a variety in the context of the Keller differential manifold. And then B is a model in the differential, in the Keller differentials model. The example that we arrive to the result will be the fact of the equivalences between of these objects, where some objects are algebras, infinite algebras, and other objects are moduli spaces. This study is given in these references. In the context of the derived categories in the level to moduli spaces for holomorphic bundles, we have this diagram. This diagram was proved in past paper and demonstrate the equivalence of these complexes, of these equations. For one side, these equations, and other side of these equations. Both equations are the field equations, and their equivalence is given by the functor, which constructed through of the integral transforms. For example, some integral transforms in geometrical analysis. For example, Penrose transforms or Radon transforms, or Fourier transforms. And the category is the solutions, the all solutions of these equations are here in this space. And there are the spectrum of these operators in the first time. And the hypercohomology to this particular case was the space. And all this study was published in this document. To demonstrate, it's necessary to define an equivalence between derivative categories in the level of the derivative categories, where geometrical motifs can be raised with the corresponding model stack to the holomorphic bundles. The integrals are those whose functors image will be in this space, as cited in this hypercohomology, and use and find the solutions of these equations in this space. This space is a spectrum of these operators under the functor defined by, for the integral transforms, where the integral transforms are the realizations of these representations in infinite representations for these operators. And in other before works also was demonstrated and obtained a classification table of these operators and their spaces, corresponding their spaces as representation. And the special case which competing is where the complexes equal Q the Q, where Q is one dimension of the complex cohomology to define the hypercohomology after the word mentioned before. And this case is obtained when of the cohomology groups of the isomorphism in cohomology groups. Additional results of Motivic cohomology, some properties of the products, the tensor products of the motifs on the vertices, complex vertices of schemes in the general case. And these schemes being smooth projective vertices for any integer one existent isomorphisms. This and this Joneda embeddings will be relevant to demonstrate we want. And resume of demonstration is the following. This category can be defined as of the motifs in hypercohomology from the category where the category is the symmetric operators with symmetric operations over K, where K is a numerical field, and the hypercohomology is finally the hypercohomology is this space. You can see the Nisnevic shifts present in our final result, though the Nisnevic shifts give a more general interpretation of the decomposing and obtaining categories, full subcategories with the same structure required. And this hypercohomology comes from the hypercohomology, where the Q is the unique service, and we obtain this hypercohomology. Our hypercohomology is this space. This space is equivalent or equal to this space. For other side, quasi-coherent shifts and derivative categories of quasi-coherent models, we have this functor. This functor is the other correspondence to demonstrate the old diagram, which have a triangulated derivative, tensor derivative structure, and proves totally the result. Some literature for these studies also you can see in the following references with more details. And that's all.